Okay, so we're going to review some questions from the electromagnetism topic. So let's start off with what happens when we put different materials in a magnetic field. So we've got two different kinds of pointers, one made of brass and one that is a magnet. And we can see we've got the field going up the page. So draw the final settled position of the two pointers. So brass is a non-magnetic material, so it's not going to do anything, whereas the magnet is going to align itself with the field, so its north pole will point in the same direction as the field lines. Okay, so explain the position of the brass pointer. Well, as I said, it's not going to be affected because brass is not a magnetic material, and so nothing happens when you apply a magnetic field to it. Explain the position of the magnet. Well, a north pole will always point in the direction of field lines, and that's because field lines go from a north pole to a south pole, so the north pole will always point itself towards the south pole because they're attracted to each other. Suggest a material from which the magnet is made. There are lots of possible ones we could go for. We're looking for hard magnetic materials, so we want like steels, cobalts, nickels, ferrite, magnetite. There's lots of examples, but definitely not iron, which is a soft magnetic material, because that would do something completely different. So the diagram shows a small uncharged copper sphere suspended from a nylon thread and a plastic rod being rubbed with a woolen cloth. The rod becomes negatively charged as it's rubbed. Explain in terms of electrons why copper is a conductor and nylon is an insulator. So copper, there are free electrons or delocalized electrons, which essentially means that electrons which are free to move around. Nylon, there are electrons still, but the electrons are fixed in atoms, so they're not free to move around. So describe how the negatively charged rod may be used to induce a positive charge on the copper ball. So as the rod approaches the sphere, the negatively charged rod is going to repel electrons in the copper sphere through the electric force because they're the same charge. So what we need to do is we need to earth the sphere with a wire so that when the electrons are repelled, they flow down the wire to ground. And then once you take away the earth, that's going to leave the copper sphere positively charged overall. So here we're not just looking to separate the charge like you would sometimes see where we put negative charge on the left and positive on the right. We want the copper to be overall positive, so we need to remove the electrons. Okay, so we've got a positively charged copper sphere. Draw arrows to indicate the direction and pattern of an electric field. It would look something like that. We need the arrows pointing away because a positive charge would experience a force away from this positive charge, and they should be equally spaced. So that's what we can see there. So the diagram shows a circuit containing a battery of EMF of 12 volts and the resistance is 6 ohms. State what is meant by electromotive force. It's the energy transferred to each coulomb of charge by a power source. Calculate the current in the heater. Well, we know the potential difference across the heater. It's 12 because the ammeter is not going to take any of the energy. So we know its resistance. We can calculate the current. State the name of the particles that flow through the heater. Well, it's going to be electrons. So draw an arrow next to the heater to show the direction of the electrons. So electrons go out of the small side of the battery. It's conventional current that comes out the large side. So calculate the thermal energy produced in 10 minutes. So we know the current and the resistance of the heater, so I'm going to use P equals I squared R. So power is 24 watts, and then energy is power times time. Converting time into seconds gives us 14,400, which is 14 kilojoules to two significant figures. So we've got a circuit where we can plug resistors between P and Q, and we've got a battery EMF of 6. Calculate the current when there's a 12 ohm resistor and a 4 ohm resistor initially in series. So in series, we can add their resistances together. And then once we can do that, we know the potential difference across them is 6. We know their resistance is 16, so it's 0.38 amps. Okay, so what if we had the resistors connected in parallel? So there are actually two approaches to this, so I'm going to show you both of them. If they're in parallel, their potential difference is the same, and it's going to be 6 volts. So we could calculate the current through each of them and then add the currents together to give you 2 amps. That's one approach. Or what we could do is calculate the total resistance, which is 3 ohms, and then do the potential difference divided by 3 to give us 2 amps again. So either of those 2 methods is absolutely. Okay, so moving on to a digital logical circuit, but we're not using the symbols, we're just using some boxes for some reason. So we've got inputs A and B connected to an AND gate, which is then goes to an OR gate, where it gets ORed with an input C to produce an output. So we need to fill in this truth table here. So if A and B are both off, D is going to be off. So we can fill in zeros for D where A and B are both off. If A and B, however, are both on, that's going to give you a D being 1. Okay, so with an OR gate, if either of the inputs is 1, so either D or C is 1, that's going to output 1. So if C and D are both 0, that gives us 0. But the next one, C is 1, so E is 1. Next one, C and D are 1, so we again get an output of 1. Draw the actual symbol for an AND gate. Well, it looks like this. So you can have them with multiple inputs, but we usually show them with 2. And then we have one output, which in this case is shown by Z. A NAND gate can be replaced by an AND gate and a NOT gate. Draw a diagram to show how they would be connected and labeling the inputs, outputs, and the gates. So we need to get a NAND gate, we need an AND gate followed by a NOT gate. So that looks like this. So we've got the 2 inputs here, we've got an output here, and we've got our AND and our NOT gate. And you have to have them in that order. You cannot have them the other way around. Describe the action of a NOT gate. Well, it changes a high input to a low output, or the opposite, it changes a low input to a high output. A thermistor, its resistance decreases as temperature increases. So essentially its resistance changes when you change the temperature, and it does that because we can change the number of free electrons when we change the temperature. So we've got a circuit that switches on a warning lamp when the temperature in an oven falls below a set value. So generally speaking, what happens is temperature drops, resistance of the thermistor increases, the potential difference across the thermistor then increases. We can work that out using our potential divider equation. So the potential difference across R decreases, which means the input at P decreases. The output then gets turned into a high output, and that turns the lamp on. That's generally. Okay, so let's put that into text. So we've got at lower temperatures, resistance of the thermistor increases, so potential difference across the thermistor increases. With series resistors, higher resistance gets a higher share of the potential difference. So that means the potential difference across the variable resistor decreases, and so the voltage at the input to the NOT gate is going to be low. And eventually it will get low enough that the output to the NOT gate turns into high, turning the warning lamp on. So what is the effect of changing the resistance of R? Well, it will change the temperature at which the warning light will come on. So if you have a bigger R, it will give a lower temperature before you actually activate the sensor.